Okay, we did a review today in class, so I went ahead and wrote the questions down for you. So I posted this document, as you see it right here, to the Schoology update. So what I'd like to do now is go through the answers. But I really want you to pause the video here and read the question and do the problems first before you take a look at my answers, because I'm going to go really quick and I want you to have your answers in front of you so that you know if you did it right or did it wrong. Don't just watch what I'm doing. There's no value in that to you, and that's not how we did it in class. So please pause the video here, read question 1, all 4 parts, do it, and then come back and check out the answers, okay? All right, so let's go ahead and let's draw some vectors. Let's go ahead. I think the acceleration vector is easiest, and I'm not going to worry at this point about the size. We know anytime we have an object moving in uniform circular motion that's rotating, our acceleration is going to be towards the center of the circle. So for the ant, the acceleration is going to look like this, and make sure you label each of your vectors. And for the dust, the acceleration is going to look like that. Okay, I know it gets a little messy to label things, but in Notability you can zoom in a little bit. For the velocity, we know the velocity is always going to be tangent to the circle. So I'm going to draw my velocity vector like this. That looks kind of tangent. I know I can't, Notability makes everything straight. Unfortunately, I can't do that in the program that I'm recording in. And then right here, our velocity vector would look something like that. Okay, so hopefully you drew something like that. So that's part A. For part B, which takes more time to rotate, the ant or the dust, hopefully you realize that they take exactly the same amount of time to rotate. There is no difference between the time it takes for the ant to rotate versus the dust. Now that doesn't mean they're going in the same velocity, but that does mean that they take the same amount of time. And it's because it's a rigid body, right? It doesn't make sense that one part of the disk would rotate in less time than the other part. Okay. Now, for part C, which has a larger velocity, the ant or the dust, we have to, and the way I always do this, I try and think of an equation. Okay, I want to think mathematically. And the equation I'm going to think about when I'm talking about velocity is 2 pi r over t. And I chose this equation for a reason. I chose it because A, it's the velocity for anything that's going in a circle. And B, I only have one variable changing at a time. So 2 is a constant, pi is a constant. T, we just said, is going to remain constant regardless of where we're at on the disk. So the only thing that's changing is this r value right here. So I can see from this that as r increases, the velocity must increase. That tells me, therefore, that the dust is traveling faster. Okay, so the dust has a faster velocity. And this is my proof right here. V is 2 pi r over t. Okay? Now, as for which has larger acceleration, the ant or the dust, proved mathematically, well, I've got a couple equations that I can consider. I can consider the centripetal acceleration is v squared r over r. That's one I could consider. But here's the problem. The velocity is changing, as we just said, and the radius is changing, as we just said, and I'm not sure which one is going to dominate. So I really like to look at just one thing on the right side changing. So I'm going to write the second equation I know for centripetal acceleration, plugging in the velocity into that equation, which I know is 4 pi squared r over t squared. Now I can look at this and I can say, well, the only thing that's changing, again, is this r value. And since r is increasing when I go from the ant to the dust, I know, again, that the dust must have the larger acceleration as well. If you have any questions on that, you should go ahead and see me. Okay, we have a similar problem here, so same rules apply. So please work on this, pause the video here, work on this, and then come back when you're ready to take a look at some answers. Okay, so I went ahead and did a little drawing to make drawing the vectors a little bit easier. And again, I think we know that the acceleration for each of these satellites, satellite 1 and satellite 2, are going to be towards the center of the circle, and they're going around, I think we said this was the Earth. So this would be the acceleration for satellite 1. This would be the acceleration for satellite 2. And then our velocity vector, it's a little tougher to draw because we haven't drawn a circle or anything here. But the nice part is that if the acceleration is pointing towards the center of the circle, then we know that the velocity vector must be tangent to the circle and therefore perpendicular. So if you drew something like this, where you said, well, this was v1, and then you draw this, and you said this was V2, that would be fine. All right, hopefully you remember for part B, which satellite takes more time to complete one orbit. It's no longer going to be the same because we do not have a rigid body like we had in our last problem. These are objects that are orbiting something, and we know from Kepler's law, specifically his third law states that r cubed over t squared is a constant. So if r increases, t has to increase as well. So that means that satellite 2 will take longer to complete its orbit than satellite 1. So which one takes more time? Satellite 2 takes more time than satellite 1. Now, when we consider which one has a larger velocity and by what factor, we have to recall some work that we did the other day. And we looked at how to find the velocity of an orbiting object. And the first thing we did was we drew our free body diagram. So if this is my satellite and this is the direction that it's pointing towards, the planet, and it's not either of these two particular satellites, but that's okay. We know that that's the force of gravity acting on the satellite. And then we did a little proof here where we said, okay, the force of gravity, well, first of all, let's write F net equals ma. Okay, and we know that the net force is the force of gravity. That has to equal m times a. But we want to do better than just writing a, because we know the satellite's going in circular motion, so we can write v squared over r. And then we know the force due to gravity is just the g times the mass of the Earth, in this case, times the mass of the satellite over r squared. And that must equal the mass of the satellite times the velocity of the satellite squared over r. And then if I do a little bit of work, I can see that v is equal to the square root of g times the mass of the Earth all over r. Well, g and the mass of the Earth are constant, so the velocity of either of these satellites is dependent on the inverse of the square root of the radius. That's a mouthful for you. So that means I know that if I increase the radius, right, if I increase the radius, I know that I'm going to decrease the velocity. Right? So right here, I know that since I've increased the radius for this second satellite, I know that this one will be going slower. So which satellite has a larger velocity? I'm going to go ahead and say that satellite 1 has a larger velocity. Now, by how much? Okay, let's take a look. If I see that the velocity depends on the inverse of the square root of the radius, I should see then that v2 has to be slower, right, than v1. So v2 is going to be 1 over the square root of 2 of v1. v1 is just the velocity of the first satellite, okay, because we said that, hopefully that makes sense. Satellite 1 is faster, right, so when I divide that by the square root of 2, I'm going to go ahead and get the velocity of the second satellite. I could do something similar for which satellite has a larger acceleration, because I know that acceleration is just v squared over r. So that's interesting because the acceleration is going to decrease by 1 over 2, the square root of 1 over 2 squared, so 1 over 4, and the radius is going to increase. So when the radius increases by a factor of 2 and velocity squared decreases by a factor of 1/2, I should be able to see that A1, or here, let's go, A2 is going to be 1 over 4, 1/4 of A1. Okay, so if you need a little help with that, take a look at this again or come in and get some help. Okay, similar to the last problem where we set up, so take a look at this, try it, and then come on back. So pause the video. Okay, similar to the last problem where we said, well, the force of gravity has to equal mv squared over r. Now we're talking about the period for a low Earth orbit satellite. So I don't like that v squared over r, so I'm going to go ahead and use g, m, and I'm going to know the mass of the Earth and mass of the satellite over r squared. Okay, I just realized that you needed some additional information here in order to do this problem, so I'm going to give you that in a second. Equals mass of the satellite times 4 pi squared r over t squared. So the mass of the satellite is going to go away, right? And I'm going to get that t squared is equal to 4 pi squared r cubed over g times the mass of the Earth. So you would have needed to know the radius of the Earth and the mass of the Earth, which, of course, I forgot to give you before we started doing the problem. So I will go ahead and give that to you right now. Okay, the radius of the Earth is 6.37 times 10 to the 6th meters, and the mass of the Earth is 5.97 times 10 to the 24th. Ooh, that's a big number. Kilograms. Okay, so you should be able to plug in and get your answer. Go ahead and pause it now. Try and get that answer now for period, and put your answer in minutes. All right, hopefully you got period is equal to 84 minutes. Now, I want you to realize something here. We assumed a low Earth orbit, and we also know that in a low Earth orbit close to Earth, don't we know the acceleration due to gravity? Isn't g just 9.8 meters per second squared when we haven't gone really far from the Earth? So instead of using this FG and this big long equation, we could have also just gone ahead and said, well, can we also just use force of gravity, mg, oh, there's my pencil, mg is equal to mv squared, mv squared over r, which means that g is equal to, well, v squared over r is just that 4 pi squared r over t squared. And then we could have used that to find the period, right? So t squared is just equal to 4 pi squared r over g. So you could have made it a little easier on yourself had you wanted to do that. Okay, try this next problem. It's pretty straightforward. I'm going to give you a hint. Go ahead and use Kepler's third law. All right, Kepler's third law says that r cubed over t squared is a constant. That means the r of satellite, the distance from satellite A to its star over the period, is equal to the distance of satellite B, or planet B, to the star cubed over its period squared. So now you can just go ahead and you can plug in what you know, and you can solve for the period for planet B. You should have gotten the period for planet B is 3.7 or 3.67, you don't round as much, years. All right, go ahead and take a look, try these graphs out, and then come back when you are ready. All right, so this first one, acceleration versus mass, hopefully you realize that you need to rearrange your equation a little bit. So I went ahead and wrote this as acceleration is equal to net force divided by mass, okay, because I want acceleration to be my y value, or my value that goes on the vertical axis, and the net force to be the value that goes on the horizontal axis, or the mass to be the value that goes on the horizontal axis. So when I do that, I can quickly see that the acceleration has an inverse proportion with mass. So a lot of you were probably tempted to draw something like this, okay? That is not an inverse proportional relationship. That's a linear relationship with a negative slope. It is not an inversely proportional relationship. An inversely proportional relationship looks like this. And you can go ahead and put the arrows on there to show it's going up and going sideways, or going up and to the right. Okay, now, acceleration versus net force, that is a proportional relationship. Okay, so in that case, you would get something that looks more like that. So the only one of these that we have to straighten would be acceleration versus mass. Now, how do I straighten that? Well, I use the equation to give me a hint. Since acceleration is proportional to the inverse of mass, right, I'm going to go ahead and graph acceleration versus the inverse of mass, and then I should get a proportional relationship. So if I went ahead and put 1 over mass here, and I can put my units in there too, but that's okay, I would get a proportional relationship like that. Okay, that's it for the review. There's also some other work that you should take a look at on Schoology, and then if you have questions, you can always see me or send an email. Thanks, have a great day.